How's that? Okay. Better? There you go. All right. Thanks for coming in to the talk, Plight at the End of the Tunnel. We'll be talking about DNS tunneling, but hopefully a lot of things that we learn here can be applied to any malicious back channel. I'm Anjum. I'm a threat researcher at Endgame. I work on problems related to network security. That generally means I work with large data sets of logs and PCAPs and such to build anomaly detection models. And so on the same tune, I've been working on DNS tunneling. So what is a DNS tunnel? Let's take this toy example. Imagine, oh man, the reds are quite dull right now. Imagine browsing to www.test.com, right? Your browser would make a DNS query for an A record for www.test.com. And over a recursive DNS query, you end up talking to the name server for test.com, which would inform you, hey, test.com is actually, www.test.com is an alias for test.com, and that's the IP address it resolves to. And that's the end of the DNS transaction. At that point, the browser goes on, makes its own IP connection to the IP, and that's it. In case of a DNS tunnel, can you guys see any of this? It's a knock-knock joke. That's my son's favorite knock-knock joke. But in case of a DNS tunnel, the domain names don't have any intention of resolving to an IP address. They can just keep going back and forth. Could we increase the red somehow? Red's. Okay. It's bright red here. So the domain names have no intention of ever resolving to an IP address. They can just keep exchanging data back and forth, arbitrary data, and that particular knock-knock joke is actually a valid DNS tunnel. What happens in real life, though, is that you can end up exchanging binary data in much large volumes if you wanted to. So let's define it more formally. A DNS tunnel is an overlay network on top of DNS. It allows you to send and receive arbitrary data between the client and a name server for that set domain. It basically means stuffing the data into a DNS packet such that it remains like a valid DNS packet and gets routed through all the middle boxes. DNS runs on top of UDP, port 53, so it's unreliable, it's connectionless. We'll soon see how that matters. You can use DNS tunneling for command and control, for exfiltration. There have been a bunch of malware families that have been using C2 for it as a C2 channel. The original DNS protocol that came out much before even I was born had the limitation of a packet size of 512 bytes. And that gives you around 800 kbps. Some more than that. Different applications have a different bandwidth, but you get around 800 kbps. In 2013, eDNS was released, which is extensions to DNS, and that allows you to that removes that limitation of 512 bytes. So it allows you to sort of negotiate hop by hop how big the packet size can be. So in theory, that gives you a much bigger bandwidth. The bandwidth, 800 kbps, isn't a lot to talk about, even though FCC might decide to call that high-speed broadband. What is it good for, right? As compared to any other tunneling, say ICMP, or there are a few other sort of lower-level L2, L3 level tunneling that you could choose. So let's look at some of the things that DNS tunnels does that stands out. Firstly, the picture we saw earlier, which you barely saw earlier, had a dotted line of connection between the client and the name server. The dotted line is actually that recursive DNS query. Your recursive resolver makes a bunch of iterative queries to these name servers in the hierarchy before it ends up talking to the name server. What's interesting in this picture is that there is never a direct connection between a client and the name server, which is the attacker server in this case. So if you had anything that did IP level monitoring, NetFlow or something, it will miss this channel altogether. If all that you were interested in was upstream traffic, in such a scenario, the server can actually just let the queries fail. It can do format error, it can do serve fail or whatever, just fail the queries so that if there is any DNS-based analytics running on the machine, on the server, it'll completely ignore that, just fail queries. So you can just let it fail if you wanted to. And all the traffic doesn't really have to go over a single domain. you can have spread the traffic over multiple domains as long as they have the same name server. So in this case, example.com, second example.com, and so on, you can have as many domains as long as they have the same name server. And taking this idea further, you can actually spread the data over multiple name servers over the same connection. So that makes this DNS tunneling quite sneaky. It's sort of low and slow, but goes under the radar quite easily. Setting up a DNS tunnel is quite easy. Took me like 15 minutes to do that. You get a domain. You have its name server pointed to your attacker's IP, and you run one of these softwares on port UDP port 53. There's at least dozens of DNS tunneling softwares out there that sort of vary in how they encode the traffic, how they encrypt the traffic, what level of encapsulation do they provide. Some do TCP, some do IP level encapsulation, some use EDNS. So there's a wide gamut of applications to choose from based on what you want to do with the tunnel. Now, DNS has been around for many, many years. I'm not going to do a DNS 101, but I'll quickly highlight a few things that are relevant to this talk. So that's a DNS packet format. The question section carries the query, and the response duplicates the query and gives the answers in the answer authority and additional section. The one thing I want to highlight here is that even though the packet format allows you to have number of questions, it's actually the protocol doesn't support more than one question in a single packet. The reason is this. Imagine if you had two questions in a single DNS query. The response will be two sets of responses in the response, but they still have to share the same set of flags. And that can lead to ambiguity in terms of how do you interpret those results. So the protocol limits it to single question per packet. The downstream, the responses can use any of these three sections. So the upstream data has to go through a DNS query, which is a domain name. The arbitrary data that we want to encode goes into the subdomain section of the query. And there are some limitations on what you can encode in that field. The domain name cannot be greater than 256 characters. It must be made up of labels that are each 63 characters or less. And most importantly, they have to have a character set of A to Z, 0 to 9, and a hyphen, underscore. I mean, domain names are case insensitive. So capital Google.com is same as lowercase Google.com. So given that we only have 37 characters to work with, in order to encode the binary data, we have to use some encoding that converts into a character set of these 37 characters. So each application has a different way of encoding that, but base 32 is quite common. The pseudocode down there is how you would go about encoding your binary data. You would base 32 encode the data. You may as well add a step of encryption at this point. And then you split the data into 255 minus the base URL's length, and take the chunk and split it into 63 byte long labels, join them together, and that's your query to make. It looks something like this. That's from DNS to TCP, from a packet capture of DNS to TCP. The downstream has a lot more options. It has three sections: the answers, the additional, and authority section to choose from. Each of those sections can have multiple resource records or RR records, and that's how a resource record looks. Our arbitrary data will go into the field, the RData field, and how we encode the data depends upon the query type. There are easily 50 or so query types in DNS. These are the ones that are most commonly used. The choice is based on two factors. What's the length limitation of that field, and what character set can we use to encode the data? Null and text are the most flexible. They let you use 2 to the power 16 characters if you want to. Text is actually case sensitive, so you have a lot more characters to work with. You can actually use base 64 encoding here and get more bang for your buck. CNAME, MX, NS, they all add a new domain name as a reference, so that has the same limitation as a domain name we saw in the question section. But these are only the ones that are used more commonly by the applications. I'm sure if you look, there is a lot more query types that you can sort of abuse to send data across. And the response looks something like this. That's the RData part of the question we sent earlier. let's quickly review the prior work in this field and see why I had to sort of revisit this topic. Back in 2012, 2013, DNS tunneling was a hot topic. There were a bunch of malwares that were using it for C2 channels. It was running. Keynote speaker at RSA spoke about it. And there was a lot of research at that point about DNS tunneling. And they all sort of narrowed down to use these features to detect DNS tunnels. The entropy of the domain, how many subdomains are under a single domain, and what's the total data transfer per domain. Unfortunately, or fortunately, depending on how you look at it, the internet architecture has changed quite a bit since then. So content delivery networks, manage their DNS not using a static zone file, but they manage it dynamically. They generate generated subdomains for their customers on the go, kill them on the go. So they generate large number of high entropy domains under their domain names. Then there are non-traditional use cases of DNS that's been growing since then. Call home. McAfee uses this way to call home, look up file reputation. Spamhaus, you can look up reputations of domain names, whether they're sending spam or not. Gstatic, DoubleClick use all sort of tracking mechanisms that's in there. So there's a lot more use cases, and the traffic looks quite weird. And lastly, the size of DNS packets have ballooned up over the last few years. And that's due to sort of this content replication, high availability. You find a DNS packet will have like 5 name server records, 10 IPv6, IPv4 records. So the total size of a packet has really gone up. And total data transfer per domain doesn't really work anymore. And if you thought you could whitelist these CDNs and so on, we have some more trouble there. So normally, when a CDN, in this case Akamai, takes over managing content for a particular website, it creates a CNAME record for the base URL and then takes over everything else from that domain onwards. That's a typical use case. There are some other use cases out there. There's this company called InstatLogic. I do not completely understand what they do, but they create these subdomains under the customer's domain, the random looking subdomains, and not just a few of them, tons of them. I think they're tracking every HTML element under the customer's domain, maybe for ad tracking or whatever. And so it's all over the place. I mean, if you look at traffic, there's so many such subdomains under completely valid looking domains. Look at the size of these labels in there. So whitelisting doesn't really scale very well anymore. So that sort of led me to revisit the problem and see what else can we do. So firstly, filtering by query type still works. There is no place for null and private queries in your DNS traffic. That's a complete no-no. The text, on the other hand, has a lot more use cases, and it's just free for all domain-specific use cases that you can provide. Originally, it was for SPF side using it. Now, document sign uses it. Domain verification uses it. So text queries are all over the place. But what still works is looking at the number of text queries under a single domain and the size of the record. Secondly, the upstream traffic has nowhere to hide. It still has to go through the domain name that's been queried. And so looking at the subdomain length of a single domain name is still a good indicator. So if you look at this graph under that, on the x-axis we have the maximum subdomain's length for each domain. And on the y-axis is the frequency of seeing that value. And that's on a log scale. Blue is benign, red is DNS tunneling traffic. And so there's a very clear boundary at around 80 where everything beyond that gets into the suspicious zone. If you add another feature to that, which is how many labels within a subdomain have length greater than 52, that reinforces that idea that that's probably suspicious. One thing to highlight here, if you look at the graph in the red, there are some DNS queries for small subdomains in malicious traffic as well. And that's because in a command and control session for a DNS tunneling, you still see a lot of small packets, control flow packets that are generally keep alive. So they do show up, but when the data transfer happens, you see these very large subdomains in the traffic. For the response, looking at the packet size doesn't work anymore, but you have to dig a little deeper and look at the R data length for each record in the response. The story is similar. The graphs on the x-axis, we have the maximum RR length, the resource record length per domain. And on the y-axis, we have frequency of seeing that value on a log scale. And 100 and above starts to get into the range where we where we start suspecting the traffic to be DNS tunneling. Look at the graph, the red, again, there's some values above 1,000. That's when eDNS was used, and you can have much bigger packet sizes there. So these two features, I'll be first to admit, are thresholds. And if somebody wanted to, they could sort of sacrifice the bandwidth and use smaller packet sizes to get under the radar. So we need to add another layer of detection in that. Before we talk about one-time queries, let's just take a step back and think from a perspective of a DNS tunneling author. DNS is connectionless, it's unreliable, right? So imagine you have two clients behind the same NAT. What you would end up seeing is packets coming from same IP address from a different port each time. It's impossible to differentiate who sent which traffic. So a DNS tunneling protocol has to add some sort of homebrew protocol on top of it to track a connection. Similarly, to be able to reassemble the packet, it has to keep track of packet ID or offset or some sort of control flow to sort of reassemble the packet that comes in. So there's some connection tracking control flow that's added to the DNS header, to DNS tunnel data. Secondly, a DNS tunneling channel doesn't want to use any stale responses. So many times they use some sort of random field in the query to make sure that it doesn't get cached in the resolver. So due to these two sort of features, none of the DNS tunneling queries are made again. The ratio of number of unique queries per domain divided by number of queries that you see is really high. In my experience, it was 0.98, and for benign, it was much lower. The really wide gap between number of queries divided by number of unique queries divided by number of queries. So that's a really good indicator. If you're getting your data from internal DNS resolver, you may also have access to the data of which IP made the query for what domain. And so uniqueness of a domain in your own network is another very good indicator for in this particular scenario. And this last feature, it sort of knocks it out of the park. It's sort of lack of glue records. So we saw this earlier as well, the CNAME example, where when a domain sets up a CNAME record, it sort of says this domain is an alias for that domain. And then either proactively or actively the client queries for the alias domain again and resolves it. It never happens that a client says, well, I'm done here, I just wanted to know it's an alias, and that's the end of the transaction. So you always have these subdomains getting resolved in one way or the other. But that doesn't happen in a DNS tunnel. If DNS tunnel has to check this box, they have to sacrifice a lot of their bandwidth to add, let's sort of tie all the loose ends, and they have to sacrifice almost half of their bandwidth per packet. So that's something that you never ever see before, see that if you track all the CNAME records, all the records with domain name in there, and see how many were abundant in the middle, that becomes a good indicator. It works with mail server records, it works with server records, any such record type that has a domain name in there. It doesn't work really well with name servers because name server records go in the additional section, which are proactively added to the records and then are not always resolved. But for everything else, it works really well. There are a few other ideas that I'm pursuing, and so they are sort of half-baked. And I just wanted to share it with you guys and see if someone wants to take this further and make this better. But in general, I don't like blacklisting something. I like to whitelist, preferably whitelist based on the customer's environment. And so I didn't like the idea of sort of looking for specific record types and say, well, these are bad to see in a network. So to look at it differently, I started segmenting the data, the domains, by a distribution of query types. What I mean by that is, if you look at this class, half the queries are A records, 0.4 are name server, 0.1 are CNAME. That's one segment, and I would group all the domains that have that sort of characteristics. And if you start grouping segmenting your domains in this manner, the malicious stuff stands out. Their signature is so different from anything else, and that's sort of, you're not specifically blacklisting a particular type. You're just understanding what's normal for your network and what's odd in your network. So that works really well in catching good stuff, but it still has a long tail end of domains that still get classified individually. So I'm sort of working on that and see how we can merge some classes. Secondly, if you think about it, DNS tunnels, only a DNS client can initiate a query. So if server has something to send to a client, there is no way, it just has to wait for the query to come in before it can respond back. So normally DNS applications do one or two, both of these tricks. One, either have the client poll frequently, or they would hold on to the last packet, last query for the longest they can, so that they can piggyback any incoming data from the OS back into response. And so these two features of a DNS tunnel make it prime for timing analysis. The polling is straightforward. You can easily DFT on the query time, and that shows up really nicely. The delayed response shows up as high standard deviation of the latency, specifically for the last packet in a query, in a chunk, in a sliding window chunk. So these two features are looking very promising. I'm still continuing to work on that, and hopefully, add those to the application soon. The future isn't pretty. There are a lot of DNS privacy protocols that are on the horizon. There is DNS over HTTPS. There's DNS over TLS that provide encryption from the get-go. So in future, it's going to be hard to detect DNS tunnels if they are using any of these encrypted DNS tools. We'll have to probably rely on the provider of these applications to do it for us. Final thoughts. I'll be releasing an open source application that you can sort of throw a PCAP at, and it'll show all the weird DNS tunneling stuff out there. It should be coming out next week. I'll work on that on the way back. The two lessons that sort of reinforce my idea about actively looking for bad stuff is it's really easy to hide in the bytes, but it's really hard to sort of look normal in the behavioral way of look normal in the benign traffic. And secondly, layered approach. One single way of detection never works. And you have multiple layers that even if one tries to evade one, like we saw with the thresholds case, there's something else that catches the bad guy. And that's it. Questions? All right. All right. Thank you.